And yes, I think we are live.
Okay, then I start with my... Hello, I warmly welcome you to our 77th webinar by the Academy of Space Renaissance International. My name is Sabine Heinz, and I'm the person responsible for our webinar series and also or one of the vice presidents. And on this 3rd of March in 2025, I'm really delighted that you have to come to join us. And our today's special guest is Dr. Andrea Lani. Hello, welcome.
Thank you for having me here. Hello.
And he will speak today about magnetic shielding for atmospheric re-entry. It's a very interesting topic, and it's the ongoing topic from our last week. We were talking about space habitats and yeah, and I also would like to welcome Adriano Ortino. He is one of our vice presidents and co-founder of SRI, and our former president. So, hello, Adriano.
Hi, hi Sabine. Welcome, Andrea, and all our audience attending this interesting webinar today. A lecture by Dr. Andrea Lani about magnetic shielding for re-entering in atmosphere. It's a quite interesting topic, and yeah, I'm very curious to listen to his lecture.
Yeah, thank you, Adriano. Andrea, before I give you the floor, I would like to introduce you to our audience, if you allow me this. Dr. Andrea Lani has a PhD in engineering sciences and a Master of Science in aerospace engineering. He's a research or team manager at KU Leuven's Center for Mathematical Plasma Astrophysics and an IAA member, co-author of hundreds or more than 100 scientific papers, and previously senior researcher at von Karman Institute and postdoc at NASA Stanford Center for Turbulence Research and NATO Science. And, my pages and science technical member. Since 20 or more than 20 years, he has led the development of model software to simulate hypersonic flows around space vehicles and space weather as co-designer of the COOLFluiD. It's a computational object-oriented libraries for fluid dynamics and ESA Virtual Space Weather Modeling Center platforms. He has been the PI of MEESST. You will explain us what it is. A large EU project, more than 10 organizations, developing the first magnetic shielding demonstrator for space re-entry. Andrea, the floor is yours. You may share your screen.
Okay, I'm gonna share my screen and then... Okay. So, as you heard, the topic will be magnetic shielding for atmospheric re-entry. This is the outline of my presentation. Before jumping directly into the magnetic shielding, I will talk a little bit about the background research that over 20 years led, or more than 20 years actually, led to this MEESST project that was mentioned. And so the starting point was the COOLFluiD project. And then I will focus on the MEESST project. MEESST stands for MHD Enhanced Entry System for Space Transportation. I will speak about the motivation of the project, the game-changing solution we propose, the consortium, the innovation that we brought on the table, some highlights of the main results. There have been many. It's been a project that ran for 4 years. And then I will conclude with some development roadmap and go-to-market. So COOLFluiD is a computational platform for multi-physics simulation. The project was started in 2002 between me and another fellow PhD student at the von Karman Institute for Fluid Dynamics, with a collaboration from the start with the KU Leuven University, where actually I'm employed now. The idea was to create a computational platform, a computational software platform that would be very flexible and also suited to run simulation on modern supercomputers, and also without putting too many restrictions on the possible algorithms, and with the intention of simulating phenomena, let's say, related to plasma or to flows, with a strong multidisciplinary and multi-physics character. So we ended up creating COOLFluiD, which is basically, let's say, an architecture in which different functionalities are enclosed in different components or plugins. And the end user is the one that actually, by, let's say, formulating a certain configuration file for the simulation, it can basically decide which module to use for what simulation. So the focus at some point had to be restricted. We could do a lot of things. We explore a lot of things, also going into heat transfer or structural mechanics and aerothermo elasticity and stuff like that. But at the end, we ended up focusing mostly on space reentry and exploration, and also space weather and solar plasma, especially during the last years. So if you look at the project, well, let's say the first official version of COOLFluiD was actually in 2003. So since then, 21 years have passed, and the achievements and longevity have largely surpassed the expectation. Originally, the project had to survive just 8 years, and now we are, 21 years and going. There have been 22 defended theses, 2 ongoing PhDs, and then here you see many postdocs, undergraduate students, 15 master theses, and so on. So more than 100 contributors from various institutions worldwide, especially in Europe, but also in the United States. And then the code is massive, is open source. We're talking about more than 1 million lines of code in C++, more than 100 modules. And this led to more than 120 scientific publications, and has been funded by more than 20 projects from different sources: European Space Agency, European Commission, US Air Force, and FWO is basically the Flemish, let's say, Science Foundation, and so on. So I, in particular, within the project COOLFluiD, apart from being the co-designer of the core infrastructure, I was also the one mostly dealing with aerothermodynamics for space reentry. So studying the flows around space vehicles, including the effects of chemistry, of radiation, and so on. So I guess all of you know that when you re-enter the atmosphere at very high speed, a hypersonic speed, you have a shock wave that forms. And behind the shock wave, due to the high pressure and temperatures, basically you get, let's say, gas dissociation, ionization. So your molecules are broken into atoms, and also you get electrons and ions that form. And all this has an impact on the, let's say, on heating up the surface of the vehicle that you have to protect. So actually, the pictures that you see here are some simulation that I did during my PhD and in the couple of years immediately after. So this was a simulation of a capsule. It was like a small version of an Apollo capsule. The project was called BLAST and was from the European Space Agency. I did a full aerodynamic study from Mach 1.3 till Mach 15, and especially at the highest Mach, I was considering also effects of thermochemical inequilibrium. So I was considering chemistry occurring because of the high temperatures. And I also did simulation for the ESA Expert, which is another project in which ESA invested a lot of effort and millions, and at the end, they didn't fly. So this capsule, which is, I think, 2.5 meters in size or something, is somewhere. Nobody really knows where. But so maybe one day it will fly. Maybe it will just stay in a museum. I also did the simulation of the Stardust, which was a capsule that went to a comet, while 2, and then re-enter. And actually, this is interesting because it's the fastest re-entry of an artificial object ever achieved. We are talking about Mach 42 and 12.5 kilometers per second in the highest point of the trajectory, which is one of the ones that I simulated. But we not only can simulate, let's say, space re-entry in terms of flight conditions, but also experiments in on-ground facilities. And there are a bunch spread all over the world, especially in Europe and in United States. At least that's where we focused. So you will hear in the rest of the presentation me talking about the Plasmatron facility at the von Karman Institute. And here you see two examples of experiments, one in subsonic flow and one in supersonic regime up to Mach 3.5. This is an inductively coupled plasma facility. It's the largest in the world of that kind. We did, let's say, when I was technical member of the NATO Science and Technology Organization, I actually participated to a couple of research activities in which we had to reproduce some experiments which were conducted in different facilities in DLR, in Germany, but also in Kubrick, in Buffalo, in United States. There was a group of people developing software like I was doing, and we compared the results and tried to match some experiments. In particular, we were looking at a double cone configuration. So imagine something like that, but rotated like with a spherical, axial symmetric. And we had experiments and basically in terms of surface pressure and surface heat fluxes. And it was not that easy to match them, but basically almost everybody matched the experiments, and especially me using a brand new solver, using also a method that was not used at the time. This is another simulation that I did with COOLFluiD. This is an unsteady simulation, so you see really the flow developing, and the experiment was actually conducted at the University of Urbana-Champaign in Illinois. We also, through a collaboration with a former colleague that worked at NASA Ames, we tried to simulate their EAST facility. EAST stands for Electric Arc Shock Tube. It's a massive facility. I think it's 8 meters in length or something like that. And what you see here is the development in time of the flow in terms of velocity, in terms of temperatures, in terms of Mach number, pressure. And you see a shock here, and actually the frame for this picture is relative to the shock. So you don't see the shock moving. In reality, you should see the shock moving and going all across the facility. You see everything happening behind the shock. But you get a picture of how complex these simulations are. And also this is more recent research, always focused on hypersonics, which is especially my core business. So we decided to basically invest in developing methods which are a bit more accurate, even though potentially less robust. And these are called high-order methods. You can visually see a difference between, for instance, a standard method, second-order accurate on this computational mesh where you see many cells, so to speak. And here, the same simulation run on a much coarser discretization and getting even better results. Because here we are running second order, here we're running fifth order. So you have high-order interpolation inside each one of these larger cells. To say it, in few words. And we did simulation of hypersonic flows. And for instance, normally people, even at NASA, to run a simple test case like this, which is a Mach 17.6 flow on a cylinder, would use much finer meshes than this. So here you see, for instance, 297 cells. Here you see 77 cells, but we are running with the 10th order of accuracy. And normally you will see something that is 100 times finer to get the same level of heat flux. We did application also to hypersonic, but considering turbulence, transition to turbulence, and trying to model really the transition. Typically, when you model transition, you get this kind of curve. So here, for instance, you are looking at the Stanton number, so the heat flux, a dimensional heat flux if you want, but would be the same if you look at the skin friction. So what you see is basically a jump in the moment in which there is transition between the laminar condition and the turbulent condition. So typically this corresponds to an increase of heat flux, which can go up to 2, 3, 5 times, 10 times. So you need to know if this occurs, because otherwise, if your thermal protection system is not designed properly in the location where you have this jump, you can have situations like it happened, for instance, for the Challenger or the shuttle when he crashed. Yeah, I mean when he exploded. And here we are simulating hypersonic flow on a cone. It was an experiment actually. So here we are comparing with experiments. And here, for instance, we are simulating a high fire vehicle, which is a scramjet. In this case, it was not flying hypersonic. We didn't consider the hypersonic condition. It's just Mach 2.6, so supersonic. But we have real flight data, and we compare with them, and we get a good match. Then another element that led us towards looking at magnetic field and plasmas was actually our involvement with modeling solar physics and space weather phenomena. And with that, we are a quite large team. Actually, there are more team members than those. Those are the, let's say, foundational members. Always using COOLFluiD, we developed COOLFluiD Corona structure, which is a solver that is able to simulate what happens in the sun, on the side of the sun, from the lower corona to the upper corona, and then we couple it with other tools that study the propagation of the solar wind, and if you have coronal mass ejections, for instance, through space to reach the different planets and the different satellites like stereo A or B or so on. And then, so yeah, we did a bunch of simulation. These simulations are data-driven. So you start with something like this, which are magnetic maps or magnetograms that tell you the distribution of the radial component of the magnetic field on the surface of the sun, or let's say close to it. And then you use that to do your magneto-hydrodynamic simulation. We also published a lot, actually 15 papers so far since 2022. And then once you actually inject, once you couple, let's say, this solver with one of those that propagate the solar wind through space, through the heliosphere, you get something like this. You see here, you have some sort of shock front that propagates and then reaches, for instance, here you have the stereo A satellite, and then there you can check if you match some observational data. So we also did predictions, like for instance, you know that there is gonna be an eclipse, or maybe, you know, you want to predict if there is an eclipse. You can do that. So in our case, we did a simulation that ran for that basically simulates what happened between the 24th of March till the 8th of April. And actually later on we compare this magnetic structure with actual observation, and we see that there is quite a match. So, you know, quite interesting research. Okay, so now we go to MHD Enhanced Entry Systems for space transportation. I will start with a video that probably is very familiar to you. We are looking at Apollo 13. And what we can say is that during this entry, you experience both intense heating on the surface of the vehicle, which actually worried the astronauts that were inside, but also a disruption of communication for, I think, 4 to 5 minutes or something like that. So when you have to wait for minutes to reestablish communication in the most critical phase of your reentry, you start getting worried. So this is kind of motivation for this project. The other thing that is motivating is, so atmospheric reentry, so the entry both back to Earth or in some other planetary atmosphere, is crucial for the success of a number of space missions. So, and these include, you know, lunar mission, interplanetary crewed mission, or uncrewed mission, unmanned mission, sample return from low Earth orbit, asteroid mining when we will get there, and so on and so forth. And you know, the more we progress with our operation in space, the more cases you will have that will need a reentry. Like for instance, now there is big hype for manufacturing in space. So at some point you will have to do more frequent back and forth from probably private space station and bring back these goods that you have produced, and probably in some cases very expensive. And of course, there is the target mission to Mars, in which Elon is heavily invested. So the problem that we wanted to address with MEESST was basically, we look at multiple critical issues that are still affecting atmospheric reentry. So, and these are basically three. One is high surface thermal loads. The other one is radio communication blackout. And the third one, which is not a problem when you re-enter in Earth atmosphere, but it can be a problem, for instance, when you go to Mars, is radiation hazard for astronauts. So we decided just to focus on two of them.
Andrea?
Yes?
Andrea, your audio is muy low. It's very low. Maybe you can put your audio a little bit higher.
Oh, this is not...
No, if you are closer, we can hear you well. No, it's better.
Now you hear me?
Yeah, now I hear you well, but it was very low.
Oh, I'm sorry. You should have, yeah, you could have told me before. I probably accidentally mess up with the, sorry. Okay, so sorry for that. So we decided to focus on the high surface thermal loads and radio communication blackout. And another source of motivation was that only in May, for instance, the NASA Inspector General found that the Orion heat shield after the Artemis 1 mission was severely damaged, as you can see in the picture, and it was possibly endangering the safety of astronauts for Artemis 2. So there is a lot of effort, also from SpaceX, for instance, in trying to design heat shields that are resilient, reliable, and in the case of SpaceX, even reusable. So there is some need to urgently seek alternative to existing thermal protection systems. One thing that I want to say is that why do you get a problem with radio communication blackout? Because when you re-enter into the atmosphere, you create this shock wave and you generate plasma, basically. Beyond the shock and all around, you create some sort of plasma sheet. And if the frequency of the signal that want to propagate in certain direction is lower than the plasma frequency, then your signal gets blocked and cannot escape. So what is the state of the art? The focus is almost exclusively on passive thermal protection systems. So passive means that you're only interested in, let's say, protecting the body. You don't do anything to change the source of the problem. And so here you see some of the concepts that are hanging around. The origami by Space Forge. There is the inflatable and flexible solution by NASA Langley. There is the 3D printing carbon-carbon by Orbital Composites. Then there is the traditional ablative materials, like the one that NASA relies upon. And all of these solutions, may work, but typically they're very heavy and they take volume. To the point that, for instance, for the Orion capsule, a significant percentage, more than 20–30% in some cases, of the heat shield, of the whole weight is taken by a heat shield. But on top of that, there is no structural solution available for tackling radio communication blackout. And so we wanted to look at something that eventually had the potential also to solve both problems, the heating and the radio communication blackout. So we looked into the magnetic shielding concept, and we tried to turn it from a science fiction idea into a scientific fact and technology. So sources of inspiration were, for instance, nature. You look at nature, you know that Earth as a magnetosphere that actually we are able to simulate with COOLFluiD, just to say, and that can actually protect the whole planet and all life on the planet from, the effects of interaction with the solar wind. And then you have the concept of energy shield, which intuitively has been around for 100 years in sci-fi first books and then movies. Then you have something more concrete, which is actually the so-called UAP, which are actually now interesting also for the Congress. They are interesting for the American Institute of Aeronautics and Astronautics, who has a dedicated team. And, there are actual data, and it's something that we have to look at. And sometimes you actually see some sort of halo around this object, especially when you look in infrared range. And then, of course, there are the principles of magnetohydrodynamics. So Magnetohydrodynamics, so actually the study and characterization of, let's say, electrically conducted fluids has been around since probably the 60s. And there was a lot of theoretical work initially, maybe some experimental. Now we can do theoretical, experimental, and numerical because we have the tools to do numerical simulations, which are pretty heavy. And before starting the project, there was already some work done by one of our partner, IRS, in University of Stuttgart, in which actually they use a permanent magnet and to try to deflect the shock and reduce the heat flux on their probe, which you can see here. So the experiment was conducted on argon, which is the simplest gas to study and to put in a facility also. And they could characterize it both with numerical simulation and with experiments. And so basically, magnetodynamics, in this case, what we are interested in is that when you apply a magnetic field to like a blunt body, for instance, like the one that you describe here, and the axis of the magnetic field, for instance, is operating here. For instance, you have a toroidal field or something like that, which is centered in the axis of the object. You generate a Lorentz force that actually has the effect of pushing away the shock from the surface of the vehicle, and that alone reduces the heat flux. But then you have to characterize how much magnetic field do you have to put to get a certain reduction of magnetic field. So a key enabling technology to actually turn this sci-fi concept into reality has been the rise of high temperature superconductors. So high temperature superconductors are, they operate a higher temperature than conventional superconductors. So instead of close to 0 Kelvin, you can go up to 20, 30, maybe even 80K. They are, let's say, they take less volume, they weigh less, they are just tape, you see, as here, and also they require less power to operate. There have been already successful application to fusion, space propulsion, and also they are investigating the application to cosmic radiation shields, which is one of the applications that I mentioned at the beginning. But in our case, we wanted to use high temperature superconductors to generate a sufficiently high magnetic field around the spacecraft in such a way that it would get beneficial benefits both for the transmission of signals and for the heat flux. Here you see a schematics of that. So the consortium was very large, 10 organizations. We were the PI. I was the PI, and it included more than 30 engineers and scientists. The budget was 3.5 million euro, and the project ran for 4 years. Initially, it should have been 3 years, but we had some delay due to COVID during the shipment of components from Russia that we couldn't do anymore, and so everything got delayed. But anyway, now it's finished. So so among these organizations, by the way, the organization from 6 different countries, and also including 4 companies. The companies are Neutron Star System, which has knowledge in high temperature superconductors, but works mostly in propulsion, and they were doing the dissemination. Then there was Teva, who was actually producing the high temperature superconductor. There was ADS, who did some assessment of radiation, and then Absolute System, who actually assembled the experimental probe, also the cryogenic system. And then we ran experiment in facilities at the University of Stuttgart, IRS, and also the von Karman Institute in this Plasmatron that I presented before. And then there was expertise in numerical modeling of plasmas from the University of Southampton, from us, from the University of Luxembourg, especially the focus on, let's say, radio signal characterization. And Keith was also responsible for the design and assembly and testing of the magnets. So we ended up let's say, what is the innovation we put on the table? Where the first high temperature superconductor based magnetic shielding demonstrator for entry. It's the first in the world. There have been experiments before with permanent magnet, as I showed you, but we are the first one that achieved this kind of experiment, especially looking at both heat fluxes and radio communication. So in the long term, or let's say in principle, the magnetic shielding idea is cost effective. So you can save payload if you can have more payload if you save in thermal protection system. You can be reusable and green. Everybody now is focused on debris or reusable system, reusable launcher, or also space vehicles. And so in this case, you don't produce any additional debris. Safer because it actively protects crew and payload. You try to remove the source or to mitigate the source of the problem. You don't not just protect the vehicle. And then is a game changer, enabling new technologies and also new kind of missions. One could think about even sending probes to the sun if you are magnetically shielded enough from penetrating an atmosphere which reaches millions of Kelvin. You would never be able to design a material to allow you that, but you can do it with a magnetic shield. Just to make an extreme example. And then, well, as a result of the project, we develop innovative software and hardware. So in terms of software, two pieces of software. One is inside COOLFluiD. COOLFluiD MHD Entry is basically, let's say, a COOLFluiD able to simulate the effect of an applied magnetic field on a chemical reactive flow, as you see around space vehicles. And then the other one is blackout ray tracer, which is a tool allowing to characterize the propagation of signal through plasmas in let's re-entry conditions. We design also innovative and test innovative hardware like the one that you see here, and we did also experiments in plasma wind tunnels. Here you see the first ever experiment we tried that was successful, that would operate at the right temperature, at the right magnetic field in the von Karman Institute Plasmatron. So we start with the manufacturing. So as I said, the superconducting tape was developed at Teva. Here you see a snapshot of it. The design was performed jointly by Teva and KIT, in particular by Sonia, that you see here. So what we did, we tried to look at different, so we already decided about the shape of the probe that we wanted to fit in both facilities. So this was a we were already limited. We had some constraint coming from what can each facility host in terms of maximum diameter, for instance. And so at the end, the best compromise was this one. We are talking about a probe which has a diameter a little above 20 centimeters. And then we had to decide, okay, now we want to see how much magnetic field we can generate, considering that we have to have, I don't know, some water cooling, we have to have some machinery in there that will take space. So at the end, we look at this multiple pancake configuration. So each pancake is basically a round of this high temperature superconductor tape. We compared 3 different configurations. One was with 5 equal pancakes. One was with 2 small and 3 large, and the other one was just with 4, but 2 small and 2 large. And we check what would be the effect of this different configuration on the maximum, on the distribution of magnetic field around the probe. So here, basically, you see in the center point, you have this value of magnetic field, and then you see at the different distances, like for instance, at 10 millimeter from the tip of the probe, you get this kind of magnetic field. On 20, you have less and less. So more or less, because of the fact that our magnet was about 30 millimeter from the tip of the probe, the value that was really interesting for us was something in between these, around 1.5. So on the surface of the probe, we, by design, wanted to have, or saw that we could have, in ideal condition, 1.5 Tesla. In reality, when we did the test of the magnet standalone, we figured out that we couldn't operate on that. We would get quench. And so basically, we would lose the superconductivity and the magnet would overheat. And so we could only operate at 0.67 Tesla as a maximum value here, around here on the plasma side. And the final solution, so since these three configurations didn't lead to any significant difference, we decided to go for the easiest to assemble, which was 5 equal pancakes, this one. During the project, we also had the chance to test for the first time a new robot that was actually purchased by Kit to wind the magnet. And actually the defect on that led to this let's say underperformance was due to a defect in the superconducting tape. There was some sort of imperfection, so to speak, and yeah, so we couldn't order a new one. We were too much close to the deadline of the project, and so we decided to go with it. The cryogenic cooling was operating with helium gas. The probe was assembled, as I said, by Absolute System, which is a French company. They basically developed everything that you see here from scratch. And in particular, if you look at the probe, you have the magnet, and then you have some water cooling all around. So we didn't put a thermal protection material on the probe itself because it was water cooled. So actually the casing is made in copper. And on top of that, we also, let's say, Kit together with the Absolute System, they design a a graphical interface like in LabVIEW to be able to monitor the performance of each individual component. So apart from the manufacturing, we also did a lot of modeling and simulation. For instance, for the radio communication blackout, we focus on analyzing some scenario, some entry, let's say, in Mars atmosphere in the ExoMars mission. So the process for doing the simulation was basically you perform computational fluid dynamic simulation, so flow simulation, including thermochemical non-equilibrium effects, around in various points of the trajectory. So we identified about 8 points that were relevant. And then for each of these, we are interested actually in detecting computing the plasma frequency. The plasma frequency depends on the number density of electrons. So we extract the number density of electron from this. And then once you have the plasma frequency inside this Borat code that I mentioned, the ray tracer, what we do is we can reconstruct a refractive index field that basically tells you that when you see refractive index equal to 0, your signal will bounce back from this dark region and will not be able to escape. So the situation is more complicated than one could think. It's not that you propagate a signal and it just goes in one direction. Actually, you have a bouncing back and forth of waves till when eventually it can escape, like you see here, for instance. So this corresponds to a situation of blackout. When you have no blackout whatsoever, ideally your signal can propagate in whatever direction, like for instance in early phases of the descent or later, like here. But when you have blackout, then you have situations like this. So the following step, once you have the refractive index, you apply the ray tracing to characterize how the signal propagate. And then eventually, as a last step, you can also compute the far field radiation, which tells you actually how much signal is left. And so we also implemented this, even though wasn't part of the project. It was done on a side project in a PhD. What you see is that if you have a situation like that, in which the signal propagates freely, you would get something like, you would get, at least in this frame or reference, something like that. While if you have a window of communication that looks like this, but if you have a blackout, your window of communication is extremely restricted. In terms of modeling, we also look at, okay, this I will skip, but too many details. So we look at entries including MHD effects. So we apply a magnetic field. We consider experiments in argon. We consider flight in air, like for instance for this OREX capsule, which was an experiment by the Japanese in 1994. And also we consider the ExoMars, which I presented before. So for instance, for the OREX capsule, So we pick a point in the trajectory. This was a Mach 17.55. We do the simulation without applying magnetic field, and then we apply a magnetic field of like 2 Tesla. And then we see, so for instance, we put a magnet of the same size as the one that we were developing, and you get some sort of effect like this, a little deflection of the shock, and in terms of heat flux, you get an advantage, let's say, of 15%. But if you put a magnet which has the size of the capsule itself, you can get up to 40%, at least for this configuration. This was an experiment in argon in which we were just looking at the shock position, the shock detachment, and there were experimental data which we could compare with, and we actually catch the experiment pretty well. And in ExoMars, we consider different configurations. So one was simply one magnet in the stagnation point. Another one was a magnet close to the aft, to the shoulder. And then another one was a combination of magnets. So one in the stagnation point and then a ring of magnets of the same size. And then, yeah, we saw that this configuration is actually the most efficient in terms of reducing the heat flux up to 30%. We did experiments. We started with a campaign of experiments to test the radio blackout. We ran these experiments both in air and CO2 to simulate both, a return in Earth atmosphere and an entry in Mars. We already use some of the numerical tools we developed, for instance, for characterizing the blackout with this ray tracing I presented before, to actually design the experiment. So we started with the experiment without the magnet, also because at the time the magnet was under production. So we had to start with something. But we wanted to characterize, let's say, how much blackout we would get if we just have a jet of plasma coming out of the facility. And we look at this configuration where we have two antennas, the side-to-side setup. The antenna was that we used was actually was operating in the K band. What we are looking at is a S matrix. So we had this vector network analyzer, and we wanted to characterize how much of the signal was propagating from antenna 1 to antenna 2 and vice versa. And this transmission of the signal is quantified by this S21 and S12 parameter. And then you also can characterize the signal that is emitted by an antenna. It comes back to the same antenna. This should not change even if you have plasma. And this is exactly what we see. So in the S11 and S22, basically we are looking at the effect on the antenna itself. There is nothing. But if you look at the others, you see that when you have a plasma flowing in the facility, the signal, basically you lose about 9 decibel in average compared to what you should get. And here, it's a picture in which you see a little more in detail this loss of signal at the antennas. We also did some numerical simulations to reproduce these results. And so this basically requires some extensions of this Borat code, of which there are more than five versions. In particular, we wanted to characterize the signal at the receiving antennas. And what we found is that we can, within some, let's say, uncertainty, we can retrieve somehow the signal numerically that is measured experimentally when there is no probe. You are just looking at what happens in a plasma jet. I mean, around the plasma jet. Then finally, the magnet was assembled. We were all excited. We placed it in the facility, and at the beginning we had problems. For instance, the magnet would not cool down to 20K, which was what we needed in order to achieve the highest magnetic field. And it took some time to fix it. Then finally, in the final setup, we managed to run these experiments. It was a matrix with a lot of tests with different electric power for the facility, different operating pressures 50 millibar, 100, 120 millibar, and also different gas, so air and CO2. We also did some numerical simulation with COOLFluiD to characterize the flow around the facility, which was needed both for the let's say numerical simulation of the blackout, but also for the experiment itself. And so what we found is, okay, so here you can see some videos, let's say, of experiments. One is in air, and 100 millibar, and the operational power is increased from 120 to 300 kilowatt during the experiment, and we are operating at the maximum value of magnetic field corresponding to 50 ampere in terms of let's say electrical current. And we do the same also in CO2. In this case, the range was between 100 and 300 kilowatt. This is the operational power of the plasma wind tunnel. It's not the operational power to power the magnet, which is around 9 kilowatt, if I'm not wrong. Anyway, so we did the experiment. First of all, we saw that there was not much difference between air and CO2. And we also saw mild effects. So when we apply a magnetic field, so the ideal situation is this one. So here we are looking at different operational power. For instance, we focus on the orange one, which is at 200 kilowatt. The pressure is the same. The operational pressure is 50 millibar. So without magnetic field, we get this behavior. And with magnetic field, we get something better. So we lose less signal. But the problem is that this result is not very consistent. It changes with the frequency. By the way, the operational frequency of the antenna that we put here in the tip of the probe is between 33 and 38.5 gigahertz. So proof of concept, but is not consistent. I mean, it's not something, you know, some effect that you are really excited about. But by increasing the speed of the flow, like for instance, if we test in supersonic conditions, and by increasing the magnetic field, not to 0.67, but maybe to 2 or 3, we believe that actually we can boost this by a lot, and also eventually we can play with the rotation. We can rotate the probe or test the magnet also in different configuration. We tried to validate the experiments numerically, and unfortunately, we were not as successful as with the case without the magnet. So actually, our numerical results are really not matching the experiments by no. I mean, we are really far. Then the most exciting part of the project was the experiments about the heat flux, which was actually our main focus. And so here you see a schematics of the facility at the IRS, so in Stuttgart University. It is basically an arc jet facility, and basically at the beginning we didn't even have the probe assembled, so we tested just on something like this. Actually, we tested, let's say, on something like this, and then numerically we also tested the geometry of the actual probe. So the operational conditions were 60 megajoule per kilogram, 80 megajoule per kilogram, and 130 megajoule per kilogram. In particular, we focus on the first two, which one correspond to moon return, and the other one to return from an interplanetary mission. So basically, the kind of data that we got are distribution of heat flux, stagnation pressure, enthalpy on the surface of the probe. We try to reproduce the experiments with numerical simulations. There is no magnet yet. And so these are the two configurations. This is the probe that you see here, and this is the original one. And we use different codes. What we see is that, first of all, we have some problems because normally when you simulate with a numerical solver that is supposed to simulate supersonic or hypersonic flow, you simulate something which is transonic. So that goes a bit subsonic, and a bit supersonic gets a bit more tricky, and we all experience the same. But somehow we got results, And we saw that the relative error on the pressure measurement was about from 0.5 to 15%, depending on the code and the conditions. And on the heat flux was from 3 to 36%. And so substantial, but depending on the case. And then this was a highlight of the whole project. This is the last round of experiments. Same facility, by the way, the name of the facility is PW-K1, and actually in IRS we only tested air, we focus on air. So what we saw, we focus on the moon return and interplanetary return condition. Here you will see how the flow around the probe, or the plasma around the probe, changes when you operate without magnetic field, with a magnetic field which is, I mean, let's say not the highest, and then at the highest magnetic field. And the operational power of this facility is actually 181 kilowatt. So you actually see basically a big detachment of the shock wave. The higher the magnetic field, the more the shock is detached, and the more is the reduction of heat flux on the surface of the probe. And in interplanetary condition, this is even more evident, actually. The only problem is that one thing that was not expected was this kind of funneling structure that you see here. So basically, this is plasma that that impinge on the stagnation point, actually increasing the heat flux in the stagnation point. And this is due to probably to a lack of isolation, electrical insulation in that region, and also to the structure itself of the jet coming out of the facility. So it's something that you wouldn't see in flight condition. None of the simulations that we did in flight condition ever shows this kind of anomaly. However, experimentally we got that, but in total, what we can see is that we get a 40% heat flux mitigation average on the surface of the probe, and in moon condition, and 80%, up to 80% for the interplanetary. We also did some simulations. These simulations were extremely challenging, also because the conditions that we used as an inflow for the simulation were not well characterized experimentally. So we didn't have the correct velocity, the correct let's say composition of the plasma, and so but even with these let's say difficulties, we managed somehow to reproduce this funneling effect, which was unexpected. Just qualitatively. Quantitatively, since we were not able even to actually converge this simulation to a final result, so we got enormous errors on pressure and heat flux. But so we will have to improve the model, but we will also have to improve the characterization of the experimental conditions at a certain point in the facility. So I'm very close to conclude. So I want to tell you a bit more about what are our plans for the future, our development pathway, and eventually the go-to market. So one thing that I didn't say is that the project has been funded by the European Innovation Council, which basically has three programs which are interrelated. One is called Pathfinder, and is to develop a technology up to technology readiness level maximum 4. And that's what we did. We brought the technology from TRL1 to TRL4, especially for the heat flux, but I would say also close to, also for the blackout, we are not too far from that. But then if you want to go to the next stage of funding, so basically bringing the technology from TRL4 to TRL5 or 6, there is another program called Transition. Less money, less partners. Basically, you have to have at the maximum 5 partners and clear, let's say, commercialization strategy and intentions. And then there is a final one, which is reserved for companies. You can only apply as a single company. It's called Accelerator. So and that would bring the product up to TRL9 and eventually even to launched product. So what we estimated is that we need about 20 million to reach the market, but the first thing that we need to do is to try to validate this technology in space, in an in-orbit demonstration. We believe we are not too far from that, and we could achieve that probably within 3 years. We already applied for a follow-up. We applied actually two proposals for this transition project, in which there was a total of 5 million involved, and we didn't get it. We got good reviews, and we can reapply next year. We count possibly also on harvesting a little bit of investor capital, people who recognize the impact that this technology can have, which is basically revolutionary for space exploration and a range of missions, which I highlight, some of which I highlight here. Of course, we will have to, develop some sort of business model and everything. So the thing is that this technology is impossible to be achieved by a single partner unless you are a large company. So the idea is to have a strong strategic partnership between 2-3 partners, one for the modeling and the marketing, one for the manufacturing or design of the cryogenic system and the magnetic and the high temperature superconductor. And then eventually, if you reach the market, what kind of markets do you want to address? So we're thinking about 3 of them. Space station cargo flights. So there is this intention to develop, and already some effort to develop R&D, products in microgravity, also do R&D. But there are companies, for instance, in pharmaceuticals, beauty care, optics, materials, superconductors, for instance, semiconductors, and then food. And then another possible market is space exploration, the most natural for lunar, especially because it seems to be the closest, in time terms, interplanetary eventually, and then reusable space vehicles. So as I said, even SpaceX has troubles, not just during the re-entry, but even during the launch, they have sometimes shedding of tiles. And, if you have a damage like that during a re-entry, it can also jeopardize your mission. But of course, there are intention of doing tourism, exploration, asteroid mining. In the long term, asteroid mining is a huge market. Some estimate this market in the quintillions of dollars. And if you go to a far asteroid and you bring back very precious metals or materials, you will really want to take that safely to the ground. And so what are the main challenges to bring MEESST technology to the market? First of all, it's a very complex technology to develop and consolidate, both in terms of software and hardware. You are pushing everything to the limit. And then you need multiple flight tests, probably needed for a small scale, maybe, and a full scale experiment, starting with the heat flux, which is the technology, let's say, the issue that we can address more comfortably for the moment. And then there is this fact that the market has been conservative since the 60s, relying on thermal protection materials. So at the beginning, one could say, okay, we can use magnetic shielding as a complementary technology to just reduce the thermal protection system. But then, if you have a lot of research and consolidation of the technology, at some point, thermal protection system may become obsolete if your magnetic shield is really so reliable. And never say never. So we have a team, expertise, tools. We have a working prototype. We are the only one in the world that can say we have a working prototype with high temperature superconductors. And we have already we had already some discussion, first with the exploration company, who is invested effort in this NYX capsule that will be one of the main access to space for Europe. And actually, they were partners in one of these projects that failed. So we will be, again, partner for the next resubmission. I also had private conversation with some people at the Thales Alenia in Turin, exploratory discussion. Eventually, if we get to test and consolidate a little bit the technology, they may have an idea how we could test it in one vehicle. Unfortunately, for such revolutionary idea, capital and timeliness, being timely are crucial to establish a game changer. And so our vision, a new era of magnetically shielded space flights and missions. And at the moment, we are looking for investments, for flight opportunities to achieve, ideally, a first flight demonstrator by 2028. So I think this was my last slide, and I'm happy to take questions.
Yeah, thank you very much for this really informative lecture, and I'm really flashed so much information. Let me just have a look into the chat. No, there was a spam, I guess. We were spammed by someone. Someone is asking, how can I join the team? Sodium X, you mean the team of Dr. Andrea Lani or the team of Space Renaissance International? Okay, there's no answer. In the meanwhile, I shall send you greetings from Bernard Foing. He's our president. He was listening almost all the time, but he had to leave to attend another event. And I also would like to remind everyone who will attend the International Aeronautical Congress in Australia this year in Sydney. The deadline for the abstract is on the 7th of March. So, will you be in Australia, Andrea?
No, I heard somebody, mentioning it, but no, I'm not going.
Yeah, okay. Adriano, I'm sure you have some questions.
Yes, of course. It's a very, very interesting presentation, and I have to be sincere. I didn't know about this technology of the electromagnetic field to protect during the reentry.
Yes.
I was aware about different technologies. Of course, the tiles is the most common, but also I heard about an inflatable mattress, let me say, to put in front of the objects. And of course, to have an electromagnetic field, it would be fantastic, avoiding any kind of thermal protection materials and so on. Let's think about this, what would be the Starship, for instance. That's such a big object to re-enter with an electromagnetic field. It will avoid all the uncertainty of the tiles, because you say that the tiles are very dangerous. Yeah. By the way, I'm seeing that you have tested your prototypes in different facilities. Well, honestly, I don't know if the plasma wind tunnel Scirocco in CIRA is still operative.
I'm not sure. I'm not sure.
By the way, I was the system integrator for that plant.
Oh, wow. Okay.
Yeah, many years ago. It was 2000 more or less, and it was a very big challenge to get that thing working.
It's a great facility, but it's difficult to make it operate. Very expensive too.
That is a real size test chamber. So I think it. I don't know. I will ask, because I still have some contacts with those people. I will ask if they would be available to test your prototype, maybe. However, okay. You anticipated some of my questions in your last 10 minutes, talking about the plans, about when you plan to have the first flight test and so on. But I was asking myself how much power supply does this system need to work?
Yeah, as I said, I think it's in the order of 10 kilowatts with the current system.
Okay.
It's a lot. It's a lot for space, but this is what is the situation.
And how do you plan to generate this power?
Now, I don't know. Some were talking about battery packs and stuff like that. I don't know if you can get to that kind of. I guess you can, but yeah, we also. I think that's the best option for the moment, and probably the requirements also in terms of power can be lowered. For instance, as you saw in my slide, the current system is just suitable for an experimental setup in a facility. You cannot put something like that, on a spacecraft. But the same company that actually developed the cryogenics has developed a compact system, or is developing a compact system which would weigh probably around only less than, let's say, between 50 and 100 kilo in total. Well, now it's like 500 kilo, this thing, So, 100 kilo, and you are talking about thermal protection system that typically weigh a ton or something, is still something competitive. Of course, then you have to see how large is your vehicle, how big has to be your magnet. The magnet itself is not too heavy. The problem is really the cryogenics. So if you solve the issue with the cryogenics in terms of volume and mass, then and also you can generate enough power, then you're definitely in business.
Okay, I see. But so if you plan to have a first test fly in 3 years, I think you're going
ideally
10 years. Sorry.
No. I said ideally, in a very ideal scenario in which we get, I don't know, 7 million euro in the next 2 years. Yeah, we could do. It's all about the money at the end.
I think you're going to implement the engineering solutions
Can you stop sharing the screen? Then we can be all seen.
Yes, I will do it.
Yeah.
Okay. Then, well, my next question is about potential applicability of this concept to not only to the re-entry, but to the protection in space from radiations, for instance.
Mm-hmm.
Do you think it can evolve toward this possible?
The concept is similar, but the configuration of the magnetic field that you have to generate is different. And so you probably have to place magnets that create some sort of spherical protection around, spherical field around. So it's just, but the technology is there. And I know that there was a group in the States funded by the NIAC program by NASA that was looking specifically on that using high temperature superconductors. So, similar technology, different configuration, and
Yeah, because there can be multiple situations. We can have villages on the surface, for instance, of the moon or Mars, and of course on Mars we don't have a geomagnetic protection field like in Earth. So it could be very, very interesting if we could, for instance, to protect a dome, a dome city with this kind of scudo, scudo term.
Shield.
And
Scudo in English?
Excuse me?
What is scudo in English? Because
scudo is scudo.
I've been talking about scudi all the time. Magnetic shield. Shield is scudo.
Yes, scudo. Scudo is what the ancient soldiers had to defend, from arrows coming. Or we can have, for instance, big rotating habitats in the on-air model, for instance, and that would also be very interesting if we could use this kind of protection, because then
But of course, you have to consider how big is the place that you want to shield. So if the place is a gigantic dome, the size of the magnet will also have to be gigantic.
Bigger.
So you don't care anymore about the volume and stuff of the cryogenic system, but still, your magnet itself has to be huge. But
Yes.
they use similar systems also for the experiments in CERN and stuff, or for fusion. Also, they rely on big magnets. So yeah, it's definitely a technology which has a lot of applications.
Quite interesting. Excellent. And
Another question?
I'm looking to my notes that I have taken during your presentation. No, okay.
Okay.
It's all by me.
Okay. So, Andrea, I again thank you very, very much for being with us. And I also would like to invite you to join us for other lectures, because our webinar series is twice per month. And so maybe you'll find some other interesting topic in our webinar series. So next week, as well in 2 weeks, on the 17th of March, we will have Marie-Louise Häuser. She is a philosopher. We also have a philosophic approach. Maybe it's not so interesting for you, but maybe, yes, you could listen. And I also would like to remind, just a second, Adriano, that we are very proud because next week or this week on Saturday is International Women's Day. And now Blue Origin sent a crew with 6 women to the moon. Also it was only with women, and they landed on the moon successfully. And I'm really, really happy that we have a woman crew on the moon. And yeah. This is very, very nice. And we should think in this, because all over the world we have regions where women have to fight for their rights. Even here in Europe, yeah, we have a lot of situations where women's rights are cutted, where women are suppressed, and yeah, and I think we still have a lot to do to have equality, and so it's more as I'm proud that we have women on the moon. And also from Space Renaissance and Space for All and Moon Mars Museum, there's some artwork landed on the moon. So that is really, really nice. So we are a non-profit organization, so we can use or need all support from you. So if you like to join us or subscribe to our video channel, yeah, I say this to all our audience, you are welcome to do so. And I wish you all a nice week and a nice evening. And I thank you for joining us, and hope to see you on the 17th of March. Okay, bye. And hasta.
I forgot.
Adriano. Yeah,
Sorry,
okay.
no, I forgot some important things that we will have, but I will write you later about that, an invitation, Andrea, because we will have in Italy in June, from 13, 14, and 15 of June, we will have a National Congress of Space Renaissance Italia. It will be in Catanzaro, at the University Magna Grecia in Catanzaro. And yeah, we will have 2.5 days discussing several things, including the space policy, Italian space policy in Europe, and what are our excellences. And I will send you an invitation if you want to join us and have a presentation in the Congress.
Will it be only in person?
No, you can also join remotely if you are not available in those days to travel to Catanzaro, but we'll be very welcome if you can join in presence. However, I will send you an invitation with the okay.
And if you join us in person and you play an instrument, you can bring it with you because we have many musicians.
I'm a drummer, but that I cannot bring with me.
Oh, that's so
Oh,
cool.
fantastic.
We still have no drummer in our team, though.
I play guitar, by the way, so we can have a jam session over
Oh
there.
yeah, for sure. But yeah, but I have to say, I probably will travel in June, but typically I travel to conferences like in United States or something. So I don't know. We'll see.
Yes, it's always a
Where are you situated? You are situated in Italy or in the
No,
United
no,
States?
in Belgium, Brussels.
Ah, in Brussels. Yeah, that's in the center of Europe, so you can
Yeah, yeah,
travel.
it's not a problem. Yeah, I can go anywhere. I mean,
Yeah, genau. Okay,
Yes,
I see you
thank
all
you very much.
in 2 weeks, and thank you again, Andrea, and yeah, I hope to see you soon or again in our activities.
thank
Okay,
you.
I wish you all a nice evening.